So in this video, we'll be talking about goodness of fit. Goodness of fit. So we had mentioned this term in a previous video also, and we had a very small discussion over there. So in here, we'll talk more deeply about this concept and why it is important. Okay. So the entire idea of econometrics is fitting the regression line in the data in the best possible manner in order to minimize the errors. Okay, so that is why this concept becomes really important. So goodness of fit of the fitted regression line to a set of data is basically how well the sample regression line fits the data. So what we hope for is that these residuals around the regression lines are as small as possible. So this is my regression line and this is the data around it. Okay, so I have to fit this line in such a way that this residual around the regression line is minimized, or the summation ui hat square is minimized. Okay, so this is a very important concept, so we'll try to understand it in the best possible way. So let me change the color of this pen. Okay, right. So we use the term r square, or the coefficient of determination determination to calculate the goodness of fit. So this is the mathematical value through which we estimate the goodness of fit. Okay, so we'll try to calculate, or we'll try to reach how we calculate this r square. So for a simple regression model, simple model, we use the term small r square. For multiple regression model, we use capital R square. Okay, just remember this notation: multiple regression model. Okay, so let's try to understand what this is meaning. So this is, suppose this is your y variable, this is your x variable. Okay, so y represents variation in the dependent variable y, and the circle x represents variation in the explanatory variable x. Okay, so suppose there is a overlap of x, this is y and this is x. Okay, this is y. So there is a overlap of x and y variable. Okay, so the overlap of the two circles, this overlap of the two circles indicates the extent to which the variation in y is explained by the variation in x. So my entire idea of econometrics is to estimate the variation in y with the variation in x. So what I try to do is the best estimate would be if the entire variation in y is explained by the x variable itself. So the ui component is minimized minimized. So this is what I want as a econometrician. Okay, so higher this overlap. Okay, this is y, this is y, and this is x. So higher this overlap, better is my estimate. Okay, so the greater the overlap, the greater the variation in y is explained by x. R square is simply a numerical measure of the overlap between the x and y variables. So your r square is basically a numerical or a numerical estimate of your goodness of fit. Okay, so the value of r square can go from 0 to 100%. So either nothing that varies in y is explained by x, or everything is being explained by x. So in this case everything is being explained by the error term, and in here everything is being explained by the xi variable. Okay, so the this is the percentage form. In numerical form the value ranges from 0 to 1. Okay, so if 1 is the value of my r square, it means that all the variation in y is explained by your x variable, and the vice versa is the case when the value is equal to 0. So more close the value to 1, so getting a value equal to 1 is like not possible, but what we can actually work for is, to get a value which is as close as possible to 1. Okay, so that my estimate or the regression line that I have is best fitted in the data, right? So let's try to calculate your r square. So what I know is yi is yi hat plus your ui hat. This is something I know. And yi is equal to beta 2 hat xi. This is small xi plus ui hat. And yi hat is equal to beta 2 hat xi. Okay, so in here, if I replace yi, sorry, so this comes from the fact that yi is equal to yi hat plus ui. So if I use this over here, I will get this equation. Okay, so yi is equal to yi hat plus ui hat. If I square both the terms, yi square or the both the sides is equal to yi hat square plus ui hat square plus 2 ui hat yi hat and ui hat. Okay, so if I sum both the sides, summation yi hat square plus summation ui hat square plus 2 summation yi hat ui hat. So one thing that I think I should explain before we move ahead, just give me a moment. So uh, this equation this equation might be a bit confusing for you, because in here I'm using your small xi. Okay, so how did small xi come here? So I'll explain this. So I know that yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. Okay, now sorry summation yi is equal to n beta 1 hat plus beta 2 into summation xi plus summation ui hat. Okay, so this is equal to n beta 1 hat plus beta 2 hat summation xi, because I know this term is equal to 0. We know this. So if I divide both sides by n, both sides by n, so I get y bar. So from here I'll get y bar, average y value, and if I get beta 1 hat plus beta 2 hat x bar. Okay, and if I subtract this equation from yi equal to beta 1 hat plus beta 2 hat xi plus ui hat. Okay, I have to subtract this from this. So what I get is yi minus y bar, which is equal to beta 2 hat xi minus x bar plus ui hat. So this is basically your small yi, and this is your beta 2 hat small xi plus ui hat. So this is also called the uh, deviation form deviation form of your regression model. So this is what I have used here. This is what I've used here. Okay, so I've used this, and from there I'm calculating these things. Okay, just keep this in mind. I hope you understood. So yeah, so now my this term will become 0 because we have assumed that these two terms are uncorrelated. Okay, so this term will become 0. So what I'm left with is summation yi square is equal to summation yi hat square plus summation ui hat square. So now I can write summation yi square is equal to beta 2 hat square summation xi square plus summation ui hat square. So where is this coming from? So I've used this thing to by I've used this formula. So this equation, this yi hat square, small yi hat square, is being replaced by your beta 2 hat xi, and that is why I get this form of the equation. So I'll also show this graphically. Okay, so this is your total sum of squares. This is your explained sum of squares, and this is your residual sum of square. Residual sum of squares, right? Why this is so? So let me try to explain this graphically. So suppose this is the regression line, and this is the average y bar value. Okay, and suppose this is your x, and given this x, your yi value is this. So now this becomes your ui hat. Okay, and since this point lies on the regression line, so this value, so this is your yi hat, and this value is your yi hat minus y bar, this value, and this value, this entire value is your yi minus y bar value. Okay, so whatever, so this yi value, yi value is being explained in terms of your two forms. So this form and this form. So so basically what we have done is we have taken the square values, because the value of yi can, either be on the upside of the regression line or the downside. So we'll, in order to reduce that, we have used the square value. So your square of the yi value can be explained in terms of the regression line. Okay, so this gap is due to the regression line. So beta 2 hat square summation xi square. So this is the explained part by the regression line. Okay, so the regression line of the sample data is explaining this much variation in the y. Okay, and the remaining is being explained by the error term, which is the ui hat term. Okay, that is summation ui hat square. So this variation in your yi, or the value of yi, is being explained by the two terms. Okay, so this is your total sum of squares. This is your summation y. So this is, and we are doing this for the entire regression line, or all the values of yi, ठीक है, that we get in the sample. So total sum of squares is equal to your explained, the part of the sum of the squares that is explained by the regression line. Okay, explained sum of squares plus your residual sum of square, and the remaining which is not being explained. Okay, right? So your TSS is basically your ESS, explained sum of square, plus RSS. Okay, so if I divide this by TSS plus RSS upon TSS, okay, so this can be written as summation yi hat minus y bar whole square upon summation yi minus y bar whole square. So you can see this from the graph also. yi hat minus y bar. yi hat, this is your ESS, this value or this term. Okay, and TSS, the total sum of squares, and this is your TSS, yi minus y bar. How far is the yi value from the um, average y value? Okay, so your r square and plus summation ui hat square upon summation yi minus y bar whole square yi. So your RSS is basically your ESS upon TSS, or R square is equal to 1 minus RSS upon TSS, which is equal to 1 minus summation ui hat square upon summation yi minus y bar whole square. Right? So R square is known as the sample coefficient of determination and is most commonly used measure of the goodness of fit. So this R square value is called the coefficient of coefficient of determination, and the most commonly used measure of goodness of fit. So basically, in this equation, this term is your R square, which is your ESS upon TS. I hope there is no confusion about this. Okay, how this R square came from, right? Is it still continuing? Okay, right. So let's move ahead. So I think this was all about your coefficient of determination, and you can also write your R square in another form. Okay, so the value of R square is non-negative. Non-negative lies between 0 say 1. Okay, so r square can also be calculated by this method, ess upon tss, this summation ui hat square upon summation, sorry, it's yi hat square upon summation yi square, which is equal to beta 2 hat square to summation xi square upon summation yi square, which is equal to beta 2 hat summation xi square upon summation yi square. So I've written this twice. Okay, it's the same thing. Just mind that. So if we divide the numerator and denominator by n or n minus 1, if the sample size is small. So in statistic, we usually do this change. So if the sample size is small, we divide the term, if you have to calculate something, by, like, supposedly the standard error or the variance, so you divide it by n minus 1 if the sample size is small. Okay, right? So then r square becomes your beta 2 hat square upon standard error, sorry, sample variance of x and sample variance of y, where your sy square and sx square is sample variance of y and x, right? So now I know that my ess, using that formula where 1 is equal to, where we had made that modification, is equal to your r square into tss, which is equal to r square into summation of yi square, and rss is equal to tss minus ess. This implies tss is equal to, or I can, which also can be written as tss into 1 minus ess upon tss. Okay, so these are just, mathematical modifications. I don't, the purpose was to introduce to the concept of r square and why is it important and what it actually means. So these formula or this modification might not be needed for you, but I just thought I'll give it to you so that you don't feel that something was left out. So this can be also be written as in this form. So your tss is equal to ess plus rss implies your summation yi square is equal to r square summation yi square plus 1 minus r square into summation yi square. So if you're given the value of uh, y square or y value or summation y value, then you can calculate your r square value using this formula also. So these are just modification and they might not be very important for you. I just brought it up because I thought maybe you needed to know this, but I think now I think it's not that important. So just forget this part, and I hope this part was a bit interesting for you, because r square is something, that allows you to check whether how your regression line is fitting in the data. So it is an important concept, and I hope it made some mathematical, statistical, and econometric sense to you. So see you in the next video. Till then, take care.